Hello, eighth grade. Welcome to another little set of homework notes. These is for the last couple pages in your note packet number 2. So these are the notes for pages 12 through 15. You've been working through this note packet over the last couple days. Here are the notes for the final pages there. So we start with a couple, we call them laws of conservation. You'll see these around a good bit in 8th grade science. And does tie into elements and atoms. And the first is the law of conservation of matter. It ties into this guy. So this guy right here, Antoine Lavoisier. You don't have to remember his name, but he was a scientist. He was actually a tax collector. He lived in France in the late 1700s, and he was a tax collector working for the nobility back then. And I don't know if you know your European history, but by the end of the 18th century, France went into revolution, and many people lost their heads, literally lost their heads to the guillotine. This poor guy, Antoine Lavoisier, also lost his head in the revolution, or in the French Revolution. But before he did, he'd also dabbled in thinking about physics, thinking about atoms and elements and whatnot. And he would do some experiments. And what he realized is if you take any combination of things and you react them, so you have some chemicals, you react them, they may turn into other chemicals, they may become other substances, but if you calculate the mass, how much you started with, you always end up with the same mass. It might not be the same stuff, but the amount of those combined stuff always ends up being the same. And so he proposed this law of conservation of matter. And he's like, you know what? I think matter, and he realized he didn't know about atoms, but in essence, he's talking about atoms. Matter, it cannot be created or destroyed. You can't make matter out of nothing, and you can't take matter and literally make it disappear. For instance, when you burn a piece of paper, it might seem like the paper disappears, but it doesn't. The atoms in that paper went through a chemical reaction and became other chemicals that mostly are smoke and kind of go up into the air. You can't see them anymore. They look like they disappear, but they don't. They're still there. They're just in a different form. So that he was saying that atoms can't be created or destroyed. What happens is they just change how they're arranged. They're just regrouped in certain ways. And so the atoms themselves don't disappear. They just get rearranged in the what we'll call molecules, how they're grouped together, molecules. They just change that away. This is also true for charge, electrical charge, when we're thinking about the electron. And that has to do with the law of conservation of charge. It's the same sort of idea. But instead of talking about atoms, we're now talking about electrons. Electrons can't be created or destroyed. They just jump from atom to atom to atom. So if one atom loses another, it must mean that another atom gains an electron. Electrons can jump to atom, but it's not like electrons come from nothing and electrons go away from nothing. In fact, all the electrons that are in you, they're in everything, all the atoms that we have, all those electrons have been around since the Big Bang. The parts of the atom, the protons and neutrons, those have all been around since the Big Bang as well. It's just fascinating how when you think of it like that. So those are the two big ideas, the law of conservation of charge. And then finally, this is something questions have been asked about this, and I was saying, like, we'll get to them in the notes, and we finally are getting them to the notes here. And that's when we think of, like, wait a minute, what's the difference between an element and an atom? And I think of it like this. So here's this page here. Elements, people knew about elements way before they knew actually what atoms were, but they were onto something. So basically, you have a substance, so any kind of substance, and that substance is made of all the same elements, all the same types of atoms. We call that an element, something that is made up of all the same types of atoms. And remember, if it's similar types of atoms, it means the same type of protons. So for example, like this is a piece of quartz, but it's not an element. There are different types of atoms in here. Actually, there's silicon and oxygen atoms to make quartz. But I have over here, this is a piece of sulfur. Sulfur is an element, which means every single atom in here is the same type of atom. They have the same number of protons. Maybe there's some isotopes in there, but the atoms have the same number of protons. You can't get anything other elements out of this substance. No matter if you break it or melt it, whatever you can do, blow it up, you still have sulfur. Other ones, like other rocks, you could melt and maybe get other elements out of it. That's why these are called compounds. But this sulfur is an element. When we think of these unique types of elements, this is going to be kind of a quick take a guess before I reveal it. So the first one, how many elements are there in the universe? I think we mentioned this before. Take a guess. 92. 92 naturally occurring elements. Fast fact, elements become more, elements are sort of built, atoms I should say, get bigger in stars. The stars like our sun can create hydrogen and helium and build them into bigger things up to iron. And then when really big stars explode, they can take elements like or atoms of iron and combine them to make bigger atoms like gold or silver or things like that. But in general, for the natural processes, we have 92 naturally occurring elements. What do you think is the most common element in the universe? You look up into the sky, most of the stars, of all the stars, all the planets, what do you think is the most common element in the universe? Give it a guess. Don't tell anyone. It's hydrogen. It's the most simple of the atoms. One proton, one electron. Sure enough, hydrogen, the most simple of atoms, the most simple type of atom, is also the most common element. And it's hydrogen that makes up the majority, makes up stars and some of the big gas planets near us. Jupiter, Saturn, those are also made a lot of hydrogen. All right, so we come down into Earth. What's the most common element in the Earth's atmosphere? Take a deep breath. What element is mostly in your lungs? If you say oxygen, not right. That's number 2. Number 1 is nitrogen. Most of the elements floating around right here in our air, the most common element is nitrogen. Oxygen comes in at number 2. Now, of course, we need oxygen. That's an important one in our atmosphere, but it's not the most common. The most common element in our atmosphere is nitrogen. What about in the crust of the Earth? Where's my globe? Oh, my globe's over there. In the crust, in the hard, rocky crust of the Earth, what's the most common element in Earth's crust? This is a trick question. You probably won't get this right. Give it a guess. What do you think? Maybe iron, maybe lead, maybe something like that. Maybe kind of aluminum, maybe. Nope. Here's a weird one. It's oxygen. Wait, what? Isn't oxygen in the atmosphere? Oxygen is in the atmosphere, but oxygen also combines to create the most common element or kind of the most common crystal that we have, the most common mineral, I should say, that we have. And those are types of minerals that are called silicates, and quartz being one. So like this is a piece of quartz. And if you look at the chemical formula for quartz, it's silicon dioxide. There's 2 oxygen atoms for every silicon atom in quartz. And since this is the most common mineral found in the crust of the Earth, oxygen being 2 to 1 is actually the most common element in the Earth's crust. Now, what about in the core of the Earth? We get down to the center of the core of the Earth. Any guesses in that? That's certainly iron. Iron, we have a solid iron core surround in the center of the Earth. Around the solid iron core is a liquid iron core that kind of spins, creates a magnetic field. That's why we have a magnetic field. And lastly, what is the most common element in you? I think we talked about this briefly. Well, you got some H2O, so you know H's and O's are in there, hydrogen and oxygen. There's a couple others. You have some carbon, certainly, some nitrogen, as well as some sulfur and phosphorus. These are the 6 most common elements in you. We have a little iron in our bloods, calcium in our bones, potassium from bananas. Don't forget to eat your bananas. Those are important as well. Some sodium and salt, definitely good salty tears, right? You have them there, but the most common 6, H2O, there's our O and H, nitrogen, carbon, as well as some sulfur and phosphorus. All right. And then 2 more pages as we go along here. And that is, wait a minute, we've talked about compounds and molecules, and I'm getting a little confused of sort of the big and the small, and I get that. Think about compounds like you do with elements, big scale. Quartz is a compound. It's stuff, and it's stuff that's made of 2 or more types of elements. So quartz can be a compound. Water is the most common compound, right? It's made up of 2 types of elements, hydrogen and oxygen. Anything that has a compound has a chemical formula that has more than one atom type in it, right? It has more than one element. And we'll see that in chemical formulas. So those are compounds. But then molecules is when we think about those compounds on an atomic level. So if we think about water, right? And we think about, all right, what is water actually made of? It's a combination of 2 or more atoms. So like if you have one molecule of water has one oxygen atom and two hydrogen atoms. So the compound, the stuff itself, in a glass, you have a glass of water, right? That glass of water is filled with water molecules. And molecules are a combination of two or more atoms. So it's sort of like a difference between thinking of it as like, what do you have on the table? Compounds, elements, kind of that scale. And then wait a minute, what are we talking on the super small scale? That's like atoms, all the same type of atoms make an element, or molecules, like it's the molecules of things that make compounds. We can see some pictures of some common molecules right here. H2O, we know what this one is. CO2, you might have heard of. As I breathe out, carbon dioxide, certainly there. This one, you can see C2, there's two C's, 6 hydrogens and 1 oxygen. And this is alcohol, like the ethyl alcohol, that's the chemical formula for it. And lastly, there's this one. Now, these pictures are kind of two-dimensional, but in our world, right, we live in a three-dimensional world. Molecules are actually three-dimensional. So here's a three-dimensional image, a model of a pretty big molecule. And this is a molecule of something. C6, 6 of those carbons. H12, there's 12 hydrogen atoms in here. And O6, there's also 6 oxygens. They combine that way to make sugar. This is the glucose, more specifically, is the type of sugar, but this is a type of sugar there. So that's sort of the way that these atoms can be arranged to create molecules. And a whole bunch of molecules together we would call a compound. Sugar is a compound, alcohol is a compound, carbon dioxide, H2O, all compounds. All right, that is the end of the notes. You made it through this packet. Great job. Let me know if you have any questions. Please write them down. Bye.